Hi. Welcome for everyone. Thank you for joining our electrical safety training session. Today, we will cover the basic knowledge of electrical hazards, risks, and control measures. Training outline. Principles of electricity. Hazard of electricity. Control measures. Emergency. Training evaluation. Exam. Principles of electricity. Electricity is the flow of electrons through a conductor. A commonly used conductor is copper wire. For electricity to flow, the conductor must be connected to a power source to form a circuit. A very simple circuit is shown in the following figure, where a battery and a light bulb are connected using copper wire to form a loop. Electricity flows in one direction around the circuit, from one terminal of the battery to the other. As it passes through the bulb, the filament in the bulb resists the flow of electricity, heats up, and emits light. If the wire is disconnected from the battery or bulb, the circuit is broken, the flow stops, and the bulb goes out. The basic parameters of an electrical system, such as the circuit shown, are voltage, a measure of the potential difference or electrical driving force/pressure that is forcing electricity through the conductor, unit, volt, symbol, V. Current, a measure of the rate of flow of electricity through a conductor, unit, ampere or amp, symbol, I. Resistance, a measure of how much a component in the circuit resists the passage of electricity, unit, ohm, symbol, R. These three parameters are linked by a simple relationship called Ohm's law. V equals I asterisk R. Hazards of electricity. The hazards of electricity are electric shock, burns, fire and explosion, arcing, secondary effects. Incidents involving electricity frequently involve two or more of these hazards at the same time. Electric shock. Electric shock occurs when a person touches a live surface and current passes through their body. Note that the electrical current passes through the body, using the body as a conductor. The current will, therefore, have a pathway through the body, from the point of contact with the live surface, where the current enters the body, to another point of contact with the ground or earthed surfaces, where the electrical current leaves the body. The most important factor that determines what the effects will be is the amount of current, amps, that flows through the body. Severe electric shock can cause involuntary muscle grip, heart fibrillation, respiratory failure, and cardiac arrest. Electric shock. The following table indicates the range of effects that might be experienced at different current flows, at 230 V, 50 Hz. 0.5 to 2 mA. At this level, the current is generally perceptible. You might feel a slight tingling sensation, but it is not harmful. This is often referred to as the perception threshold. 2 to 10 mA. In this range, the current can cause a painful shock and muscle contractions. You might still be able to let go of the source of the current, but it can be quite uncomfortable. This is sometimes called the let-go threshold. 10 to 60 mA. Currents in this range can cause severe pain, muscle contractions, and difficulty breathing. The risk of ventricular fibrillation, a life-threatening heart rhythm, increases significantly. This is considered a dangerous level of current. Above 60 mA, currents above 60 mA can cause immediate and severe effects, including cardiac arrest, severe burns, and potentially fatal injuries. The likelihood of death increases with the magnitude of the current. Several factors influence the severity of injury associated with receiving an electric shock. Voltage, the higher the voltage, the greater the current. Duration, the length of time that a person is exposed to the flow of electricity is critical. Frequency, of the AC current. Current path, the route that the electricity takes as it flows through the body is also critical. Resistance, the higher the resistance, the lower the current. Contact surface area, the more skin that is in contact with the live surface, the lower the resistance and the more severe the injury. Environment. Any environmental factors that reduce resistance will cause an increase in current flow and therefore increase the severity of the shock, e.g., wet surfaces, humid air, metal surfaces, etc. Nature of the clothing and footwear may provide some protection. Presence of potential secondary hazards can result in additional injuries, e.g., if working off a ladder the person may fall. Electric burns. Burns. Burns can also result from an electric shock, at the point of contact and at the point that the current flows out of the body. There may also be internal burns along the current path. First-degree burns. These burns affect only the outer layer of the skin, epidermis. They cause redness, mild swelling, and pain, similar to a sunburn. The skin may peel as it heals. Second-degree burns. These burns affect both the outer layer, epidermis, and the underlying layer, dermis, of the skin. They cause redness, swelling, pain, and blistering. The skin may appear shiny and wet. Third-degree burns. These are the most severe burns, destroying both the epidermis and dermis, and extending into deeper tissues. The skin may look white, blackened, or charred, and there may be little or no pain due to nerve damage. People receive burns in two different ways during electrical incidents. Direct electrical burns, where current causes overheating as it passes through the skin and the internal tissues of the body. There may be entry and exit skin burns, and these will be full skin thickness. The internal tissue burns can be very severe and may prove fatal. Indirect electrical burns, which do not occur as a result of current passing through the body, but when an electrical incident causes something to overheat and explode. For example, dropping a spanner onto a high-voltage cable can cause a short circuit which results in a flash of radiant heat and an explosion of molten metal. Fire and explosion. Fire and explosion. Electricity can cause fire and explosion in several different ways. Electrical equipment may be faulty and overheat as a result, leading to a fire. The system may be overloaded, as too much current passes through it overheats. Equipment may be misused, e.g., it may be connected into the mains supply by pushing bare wires into the socket rather than using the proper plug. A flammable atmosphere may be present which electricity ignites. Electrical equipment may produce heat or sparks as part of its normal operation. Static electricity. Static electricity. Static electricity refers to the presence of an excess of electrons on one surface, or in a material, relative to adjacent surfaces or materials. In this way, a potential difference can build up between objects that are relatively close together. For example, when you rub a latex party balloon on a woolly jumper, you transfer electrons from one surface to another, and this creates a static charge. The static is actually produced by a buildup of electrons on poor conductors of electricity. Discharge of static from a person is rapid, less than 3 milliseconds, likely to cause some discomfort, but unlikely to cause burns or a fatality, although it may cause a secondary accident such as a fall from height. Little risk exists to a person from the normal static shock found in most workplaces unless there are flammable liquids or flammable atmospheres present. There is then the risk that the static shock will ignite the liquid or atmosphere, causing fire or explosion. Arcing. Arcing can occur when the potential difference between 2 points is great enough to create a conductive path between them. The resulting arc will be capable of crossing the air gap or insulation which separates the two. Very large amounts of energy can be created in a short time, usually less than 1 second. For example, if a steel scaffold tube is placed close, as little as 10 centimeters, to a high-voltage power line, at 11 kV, then an electric arc will be struck between the power line, at high potential, and the tube, connected to the earth, so at zero potential. Electricity will flow through the tube and anyone holding the tube. The resulting shock would probably prove fatal. Even being close to such an arc is not without risk. Arcing generates ultraviolet radiation which can burn the skin and the retina of the eye. Additional burns may result from radiated heat and from molten/hot metal fragments/splash. The dangers associated with arcing increase at higher voltages because the distance that electricity can arc through air is determined primarily by voltage. The higher the voltage, the greater the distance. The main risks associated with arcing are Electric shock as a result of being struck by the arc. Direct burns as a result of being struck by the arc. Indirect burns from the radiant heat given off by the arc and from the melting of any equipment struck. Damage to the eye as a result of the ultraviolet light, UV, that is emitted by the arc. A scaffolding company was prosecuted by the UK HSE and fined £80,000 after a worker, who was erecting scaffolding in December 2016, lost 4 limbs as a result of being electrocuted. The company director was also sentenced to 6 months in prison, suspended for 12 months. The court heard how, when the structure came into contact with 33,000-volt overhead power lines, the worker received an electric shock which resulted in such severe injuries that surgeons had to amputate his left arm above the elbow, right arm below the elbow and both of his feet. He also suffered severe burns to his legs and back, damage to his vocal cords, and was in an induced coma for 6 weeks. Working near the overhead lines. Working near the overhead lines. Although out of reach under normal circumstances, overhead lines, which are not normally insulated, can become accessible to those working on roofs, scaffolding, or elevated platforms. People operating vehicles such as cranes and excavators, or handling equipment such as scaffold poles, metal ladders, or pipes, can also be at risk due to contact with, or arcing from, overhead cables. Approximately a third of accidents involving overhead lines are fatal. Contact with underground power cables. Contact with underground power cables. Both low voltage, less than 1000 V, and high voltage, greater than 1000 V, power cables are routinely buried in the ground. When electrical cables are struck during excavation work, this can lead to electric arcing, shock, burns, and fire, not to mention major business disruption to service users. Cables can be struck using hand tools such as spades and pneumatic drills, and by mechanical excavators. Note that it is not necessary to sever a cable or cut completely through the insulation to the cores inside to cause damage. Crushing the cores of an armored cable can be enough to cause catastrophic arcing and explosion. Secondary effects. Put simply, the secondary effects are any sort of injury that results indirectly from receiving an electric shock. Common secondary effect injuries occur when people undergo violent muscle contractions during an electric shock incident. They may be thrown across a room and receive cuts, bruises, and broken bones as a result. If they happen to be working at height off a ladder, then even a relatively minor shock can cause enough of a reaction to cause a fall. Portable electrical equipment. Portable electrical equipment. Causes of portable electrical equipment incidents. Using unsuitable equipment, e.g., the use of non-intrinsically safe equipment in a flammable atmosphere. Using equipment in wet, damp, or humid conditions. Misuse, e.g., sticking wires directly into a socket rather than using a plug. Physical abuse, e.g., pulling the plug out by tugging at the flex, carrying the tool by the flex, allowing the flex to be pinched, trapped, or crushed, driving over the flex, etc. Portable electrical equipment. Causes of portable electrical equipment incidents. Repairs carried out by unauthorized personnel or carried out badly, e.g., split flex taped up with insulating tape. Continued use of faulty, defective equipment. Chemical damage to the flex, e.g., by corrosive wet cement. Lack of routine inspection, testing, or maintenance. Control measures. Protection of conductors. Protection of conductors. Electrical conductors should be protected by insulation so that a person is not exposed to a live conductor. For example, cables should be insulated by an unbroken, undamaged sheath so that the live copper conductors are never exposed, and the casing on a drill should be intact so that the user cannot make contact with the live components within. It is essential that equipment is inspected and maintained to ensure that the insulation and protective layers are not damaged, and that where access may be possible, for example via an electrical panel or switchgear, the access doors are locked and controlled. Selection and suitability. Selection and suitability. Electrical equipment must be carefully selected to ensure that it is suitable for the electrical system that it will become a part of, the task that it will perform, and the environment in which it will be used. No electrical equipment should be put into use where its electrical strength and capability may be exceeded and give rise to danger. It should be able to withstand normal, overload and fault currents. It should be used within the manufacturer's rating and in accordance with any instructions supplied. If the equipment might be exposed to hazardous environments, then it should be constructed and protected to prevent danger. The following hazardous environments should be taken into account. Whether equipment and cables may need to withstand exposure to rain, snow, ice, wind, dust, and lightning. Natural hazards, e.g. solar radiation, plants and animals, e.g. gnawing of cables by rats. Extremes of temperature and pressure, e.g. heat from motors. Dirty conditions, contamination by liquids or solids. Corrosive conditions, caused by chemicals. Liquids and vapors, immersion, splashing or spraying with water and solvent vapors, etc. Flammable substances, e.g. flammable gases, dusts and vapors. Protective systems. Fuses and miniature circuit breakers. A fuse is a device used to prevent current overload. A simple fuse is made up of two metal caps joined by a thin piece of fuse wire. When this fuse is incorporated into an electrical circuit, current flows through the wire. If the current is too great for the fuse wire rating, then the wire becomes hot and melts. This breaks the circuit. Miniature circuit breakers, MCBs, are electromechanical devices that work in a similar way to fuses to protect equipment from current overload. One significant difference is that an MCB does not melt in response to current overload, it simply trips out and can be reset by pressing a button. Earthing. Earthing is a way of protecting equipment so that in the event of an electrical fault, current flows safely to earth rather than flowing through a person who might be touching the equipment. The earth wire of an item of electrical equipment is usually connected to the outer metal casing or chassis of the equipment. If a fault develops and the casing or chassis becomes live, then a current will flow down this earth wire. Electricity always takes the path of least resistance, and since the earth wire will have very low resistance, the majority of fault current will flow safely to earth through the wire. Any person touching the casing will receive a minor shock. Isolation. Isolation is the removal of electrical power from a circuit or system. This might be achieved using a switch isolator or by pulling the plug out. This makes the system or circuit dead and safe to work on, unless electrical energy is stored in the system. To ensure safety, isolation should always be physically secured before people work on the dead system. This is often achieved by padlocking isolators in the off position, the lockout-tagout system. As an additional precaution, the system should then be tested to prove that it is dead. Residual current devices. A residual current device is specifically designed to protect human life in the event of electric shock. It does so on the basis that it is very sensitive to small current imbalance in a circuit and is able to break the circuit very quickly. The principle of an RCD is that it constantly compares the amount of current flowing down the live and neutral lines, and if an imbalance is detected, it trips the circuit. Double insulation. The principle behind double insulation is exactly as suggested. There are two layers of insulation between the user and any live conductors. This eliminates the need to provide earth protection, so double insulated equipment will have a two-core flex, live and neutral only. Double insulation is commonly used as the means of protection for handheld portable electrical equipment such as hedge trimmers. Competent persons. Where work on electrical systems creates danger or risk of personal injury, then the employer must restrict that work to those people who have the necessary technical knowledge or experience to be able to carry out that work safely. In this context, a competent person has knowledge of electricity, experience of electrical work, an understanding of the system to be worked on, an understanding of the hazards and the precautions needed, the ability to recognize whether it is safe for work to continue. The extent of personal knowledge and experience needed will have to be decided by the employer. It may be that these requirements can be relaxed provided an adequate level of supervision is being applied, e.g., an apprentice electrician can gain experience provided they are appropriately supervised. Permit to work, PTW. Permit is required to enter the electrical/switchgear room from the electrical department. PTW should be issued for any electrical maintenance works. Working on live electrical sources prohibited without written approval by the HSE department and approved risk assessment has been prepared. Working near the overhead lines. Working near the overhead lines. Prevention of accidents associated with proximity to live overhead power cables can be achieved by isolating the power supply when working in the vicinity of power lines, using SSWs and permit systems to control access into danger areas, using barriers, signage, and goalposts to keep plant and vehicles a safe distance from power lines, using banksmen when a plant is maneuvering near power lines, using non-conducting equipment, such as fiberglass ladders. Inspection and maintenance. Inspection and maintenance. Electrical installations and equipment should be routinely inspected to ensure electrical safety. This includes the electrical equipment installed in the buildings, such as power distribution circuits and lighting, large items of electrical equipment that are not moved, smaller, portable appliances. Things to check during routine visual inspection of a portable appliance. The body of the appliance is intact. The body of the plug is intact and secure. The plug cable clamp appears to be tight. The cable appears fully insulated, with no splits or severe kinks/pinches. There are no obvious scorch marks to the plug or appliance body. The plug and appliance are not wet. PPE. Energized, live, electrical work. Insulated gloves, protects hands from electrical shocks and burns. Safety glasses or goggles, shields eyes from sparks, debris, and arc flashes. Flame-resistant, FR, clothing, reduces the risk of severe burns from arc flashes. Face shield, provides additional protection against arc flashes and flying debris. Hard hat, protects the head from impact and electrical shock. Insulated tools, prevents accidental contact with live electrical parts. Electrical safety shoes, provides insulation from the ground to prevent electrical shock. De-energized, off, electrical work. Insulated gloves, still necessary in case of accidental re-energization. Safety glasses or goggles, protects eyes from mechanical hazards and debris. Flame-resistant, FR, clothing, provides protection in case of unexpected arc flashes. Hard hat, protects against impact and potential electrical hazards. Insulated tools ensure safety when working near potentially live parts. Arc Flash PPE. Emergency procedures. A careful assessment of the situation is needed when approaching the casualty. This is important for two reasons. The casualty may still be receiving an electric shock, in which case touching them will involve their potential helper in the shock as well. High-voltage conductors can arc electric current through the air over large distances, meters, as discussed earlier. In order to provide appropriate casualty care, do not touch the casualty. Call for help and an ambulance. Turn off the power supply. If the power supply cannot be switched off, then carefully push or pull the casualty away from the live part using non-conducting material, such as timber or dry clothing. Check breathing. If the casualty is breathing, place them in the recovery position. If they are not breathing, apply cardiopulmonary resuscitation. Treat any obvious burns. Treat for physiological shock. Make sure they get professional medical treatment. Heart problems and internal burns may not be apparent to the casualty or first aider. High-voltage conductors can arc electric current through the air over large distances, over 10 meters. For electrical fires involving live equipment, it's crucial to use the correct type of fire extinguisher to avoid the risk of electric shock. Suitable fire extinguishers. CO2, carbon dioxide, extinguishers, these are ideal for electrical fires as they do not leave any residue and do not conduct electricity. They work by displacing oxygen, which helps to smother the fire. Dry chemical powder extinguishers, these extinguishers contain non-conductive chemicals that can effectively put out electrical fires without the risk of electric shock. Unsuitable fire extinguishers. Water-based extinguishers, these should never be used on electrical fires because water conducts electricity, which can lead to electric shock and potentially spread the fire. Foam extinguishers, similar to water-based extinguishers, foam can conduct electricity and should not be used on electrical fires. If you have any questions, please contact Adirad Mining Company HSE Department at any time for clarification. Training evaluation. Please use the QR code to reach the evaluation link, or you can find it in the attachments of this video. Exam. Please use the QR code to reach the exam link, or you can find it in the attachments of this video. Thank you.